Hi everyone, this is Yading Yuan from Mount Sinai Hospital in New York. Today I'm going to report our solution to this year's Brain Tumor Segmentation Challenge. We participated in this challenge by further evaluating the scale attention network, which we previously developed for image segmentation on a larger dataset. This is an overview of scale attention network. It follows a typical encoding and decoding design. The encoding pathway is built upon RSNA. In order to further improve the representative capability of the model, we added a squeeze and excitation model into each residual block to form a RSI block. The decoding pathway follows the reverse pattern as encoding 1. The upsampled feature maps are then added to the output of scale attention block. Here, we use summation instead of concatenation for information fusion. We also use deep supervision at each intermediate scale level to regularize the model training. Now let's take a closer look at the scale attention block. As an example shown here, if we want to fuse the information at the second decoding scale level, we first reshape all the encoding outputs to the same dimension by either downsampling or upsampling. So this part is designed to learn the contribution of each scale in each feature channel, and the final output is the weighted sum of these features from different scales. Here are some implementation details. Our model was implemented with Python using PyTorch on NVIDIA 1080 Ti GPU with 11 GB memory. We used the simple ITK for reading and writing images. And for pre-processing, we used instance standardization and trained the model with randomly sampled patches with a size of 128 cubic. We relied on 5-fold cross-validation to develop and optimize our model. Training the network took 300 epochs from scratch using Adam. Learning rate decay and early stop were used when validation loss stopped decreasing. We used group normalization with batch size of 1 and used dropout and several data augmentation strategies to reduce overfitting. We generalized the Jakarta distance loss, which we developed in our previous work, to multiple objects and combined it with focal loss to further learn from those difficult voxels. So during testing, we firstly applied the sliding window to extract 8 patches around the brain region, then extracted the region that included the whole tumor for another inference. We averaged these outputs and applied the threshold of 0.5 to obtain binary masks for whole tumor, tumor core, and enhanced tumor respectively. So we first compared ASNR with RSI unit in 5-fold cross-validation using the training data from last year. The only difference between these two models is the RSI unit uses a scale-wise escape collection, while ASNR uses a scale attention block for multiple scale information integration. As we can see, ASNR consistently outperformed the RSI unit in different folds, with an average 1.5% improvement with 7% less parameters. So these are the results of the 5-fold cross-validation on the training data sets. For comparison, we also listed the results we obtained from last year. It is clear to see the segmentation performance was significantly improved with larger data set. So here are the results when applying the models to the validation sets. We can see the improvement was especially significant for enhanced tumor. So for the final submission, we also included the models trained from another 2 variants. So the first one, we assigned different seeds for different folds, and in the second variant, we reshuffled the training cases and evenly distributed the cases without enhanced tumor to the 5 folds. So eventually, we used the average outputs of 30 models as the final prediction. For each case, the prediction took about 2 minutes in our experimental environment. That's all. Thank you for your attention.